Hi, I'm Ines, and in this talk I'm going to share some lessons we've learned about solving NLP problems in an industry context. A lot of the discussion in the NLP community today is being led by academic researchers, which does make sense in many ways, given that these are young technologies that are still improving quickly. However, academic researchers naturally focus on questions that generalize, but in any actual project, a big part of the process and planning will be done afresh every time. It's those parts that don't generalize that get lost from the conversation. And those are the things I want to highlight today. First, let's start with a quick intro. Some of you might know me from my work on spaCy, a popular open source library for industrial strength natural language processing in Python. spaCy was first released in 2015, a bit over 5 years ago, and we've been very happy to see the project grow over the years. It's always a bit difficult to estimate usage of open source libraries, but spaCy has been downloaded over 17 million times, with currently 1 million a month. Over 400 contributors have submitted pull requests to the project, and we've been especially excited about the growing ecosystem around the library, with currently over 80 community-developed extension packages and plugins for a variety of NLP tasks. In 2016, we founded our company, Explosion. We initially raised what we call a client round, and for the first 6 months, we did a bit of consulting to bootstrap the company. Since 2017, we've been entirely funded through software sales, and we've been able to build an amazing team over the years, all while staying 100% independent and profitable. Our first commercial product is Prodigy, a modern annotation tool for creating training data for machine learning models. It's fully scriptable in Python and lets you build powerful, semi-automated workflows and even put your model in the loop. Prodigy now has a very active community and over 4,000 users, including over 500 companies from a variety of different industries. As a developer tools company, one of the things we care about is developer experience and providing a stack that helps developers deliver more successful projects. We've seen a lot of projects, and one thing you can see across all of them is that they fail a lot. If you've worked on NLP or even just machine learning before, it's probably something you can relate to. You try a lot of things and most of them don't work. But even aside from subjective experiences, it makes sense that a lot of projects fail. The PR you hear might tell you otherwise, but just imagine what a world would look like if NLP didn't fail a lot. We'd be able to automate a lot more tasks, assist humans better, and analyze text for more interesting insights. But it's just not that easy. However, there are some things we can do to improve the success rate of our NLP projects, and it all starts with the workflows you choose and how you design your systems and applications. Instead of trying to pinpoint what it is that makes a project successful, let's turn the question around and ask ourselves, how can we maximize a project's failure risk? Which steps can we take to make sure it definitely fails? Many great failed projects start with imagineering. Manifest your NLP system by imagining it. When you decide what you want your application to do, be ambitious and think big. After all, you want to change the world, and you shouldn't let reality limit your possibilities. Think unicorns flying towards an upward curve. Before you start implementing your failed project, you also need to forecast and decide what accuracy you need. After all, that gives you a concrete and quantifiable goal to work towards, right? 90% is always a good number because it's pretty high. Maybe you can even go a little higher if you're planning on doing something state-of-the-art. Now that we know which accuracy we want, we can pay someone to create the data for us. It's a shame we can't just ask for data that gives us 90% accuracy, so we just ask for 10,000 rows. Now it's time to wire everything up. This is the fun part, and you've probably been looking forward to this the whole time. And it's what people typically think of when they hear machine learning. You can really go all in here, try out the latest techniques and tools, and see how many layers and parameters you can come up with. And finally, once you're done, ship it. Hopefully it works, fingers crossed. If not, we can probably find someone to blame. The thing is, as much as we like to talk about failure, so inspiring, it also really sucks. Yeah, you can learn from it, and it makes for a good Medium post, but if you have a choice, you might as well not fail, or at least minimize the risk of failure. So, why is there so much risk of failure at pretty much every step of the way, and how can we minimize it? Well, one issue is that we end up with a very tricky chicken and egg problem. In order to come up with a product vision and make sure it's viable, we do need at least some sort of estimate of the accuracy we'll be able to achieve. We'd have to design our system very differently if the model was only able to achieve 80% accuracy on a specific problem, as opposed to 95%. For example, in conversational applications, there are lots of clever ways to design the flow and user experience around potential mistakes that the model makes, which it probably always will. But if we want to make those decisions, we need to start interacting with the data, and we need to run some training experiments. And we can't really do that before we have at least some labeled data. But to label the data, we need to know how our annotation scheme should look and what we want to label and predict. And that always depends on a product vision. So the problem is, where do we start and what do we solve first? And what happens if one of those components changes? The solution is, instead of just iterating on the code, we need to iterate on the whole development process, especially on the data. The nice thing about training data is that it lets us define what we want the model to learn and how the system should behave. That's great, and it gives us a lot of power. Iterating on both the code and the data allows us to try out different ways of framing the problem until we find the approach that works best. Here's one of my favorite simple examples. If you're working as a developer or data scientist, you're often tasked with solving specific business problems. In this case, the system should help with building a crime database based on news reports. It should be populated with the name of the victim, the perpetrator name, the crime location, the date the offense took place, and the date of the arrest, if available. So these are the types of information you need to extract from text. So here's the obvious way to break down the task. You could annotate the types of information you're looking for as spans in a text, and then try and train a model to replicate those decisions. For instance, Alex Smith would be annotated as victim and East London as crime location. This clearly meets the requirements. However, is this really the best way to break down the problem that can be predicted reliably by the model and that you can create data for cheaply? Maybe not. In order to make accurate predictions here, the model has to identify that the text is about crime and that East London in this exact context is a crime location, but that King's Cross is not. There's nothing that inherently makes the phrase Alex Smith a victim or East London a crime location. Here's another way you could break this down that takes advantage of what the model will likely be much better at: predicting consistent generic entities like person or location based on the surrounding context, and assigning labels to text describing its topic. This annotation scheme can still let you extract the same information from the text, even though it doesn't translate the business requirements into a model one-to-one. You just need to connect the pieces of information. Even though syntax trees may have become slightly uncool over the years, they still have a big advantage. They can generalize very well, and they're less domain dependent. If you can accurately predict the syntactic dependencies, you can extract the relevant relations in your text. For instance, that Alex Smith is the passive subject of the trigger word stabbed, indicating that they were stabbed, and thus the victim. And it shows East London attached to stabbed via the preposition in, indicating the location. Here's another example of a problem you may get tasked with as a data scientist. Your company has an internal database and analytics and wants to connect that to information about the latest company sales from financial news. You'll need to find the buyer and the company that was bought with their official company name so they can be resolved to your database. You also need the stock tickers if possible and the sale price and currency. So, how do you approach this? The thing is, your company's requirements usually don't map to something you can predict end to end. So it's your job to take the business problem apart and convert it into machine learning problems that can be solved. Ideally, cost-effective, efficient, and with a high chance of success. So how can you break this down? Here's one example of a sentence and the structured information we want to extract from it. Microsoft acquires software development platform GitHub for $7.5 billion. Buyer is Microsoft, target is GitHub, price is $7.5 billion, currency is US dollars. But how do we get from the raw text to the structured output? Can't we just find some fancy language model with lots of parameters and predict it end to end? Well, imagine all the steps it would need and the amounts of data it needs to see. And if it gets one piece of the syntax wrong, your whole result is broken. And if you need to extract more information, you need to train everything again from scratch. And don't forget the hyperparameters. Instead, here's a more sane approach that you'd likely choose over the other. First, the data you're working with is probably noisy, so you want to make sure you're only analyzing texts that are actually about company sales. So the first step could be to train a text classifier to predict company sale. Next, you need to find the buyer and target company and the sale price. This could be solved by a named entity recognizer trained to predict org, or maybe buyer and target, and money. The entity recognizer will only be able to extract phrases that actually occur in a document. So in the next step, you could train an entity linker to map mentions like Microsoft to a real-world entity and node in your knowledge base, like DBpedia or an internal database. For public companies, you also need the stock tickers. There's no reason those need to be predicted. Once you have the knowledge base entry and the full company name, you can look those up in a directory. Finally, the prices need to be integers that you can do maths with. There's probably an existing Python library that you can use for currency normalization. You could also use article metadata to determine that it's US dollars, for instance, because Microsoft is based in the US. And here you have it, the structured output and idea for a processing pipeline that could produce it. Whenever we look at real-world use cases, it becomes clear that reality just isn't something you can predict end-to-end. And trying it wouldn't make sense if we have many other techniques available to solve specific problems. It wouldn't make sense to generate the structured output with a sequence-to-sequence model. That would be highly impractical, not very scalable, and it would just make your life much harder. The great thing about practical and applied NLP is that you can choose to make the problem simpler if your solution isn't working. It's easy to forget that while following a lot of the research, where it's obviously not an option to just change the task and objective while comparing algorithms. But if your goal is to solve a business problem, you can frame the task so that it's easier to learn, with higher accuracy, cheaper to annotate, and cheaper to train, and faster to develop. All of these are things that typically increase the rate of success. Some of the most interesting business problems that people are trying to solve are very specific. Specific to the company, specific to the internal documents, specific to business activity. Otherwise, there wouldn't be much value in them. Why would you hire data scientists, developers, and analysts if you could just download a magical pre-trained model off the internet that can just answer all your questions for you? If that were the case, there'd be no value in what you're doing, and you'd probably be doing something else. Also, many people still assume that training a model needs millions of examples and that this is just not viable and too much work. But that's not really true anymore. Big data is a nice buzzword and it sells well, but in reality we might only need a very small set of examples specific to our problem. We might not need many, but we do need some. Transfer learning can make a big difference here. It's like training a new employee who already speaks the local language and understands the general concepts of the work and just needs to learn about the specifics, versus raising a new employee from birth. The latter is inefficient and also pretty disturbing and probably illegal. Anyway, no matter how many parameters your language model has, it's not going to magically solve all your business problems for you. If your problems are specific and valuable, the easiest way to program a model's behavior is to provide a small number of specific examples and to combine different NLP techniques. Given how quickly NLP has been improving in the last few years, it's reasonable to be thinking about how things might develop. We want to have workflows and approaches that we don't have to keep discarding and reinventing. So let's turn this around and think about what won't change. One of my answers is that we're still going to want to tell the computer what to do. It's what the software industry is all about. AI technologies are different means, but the end, programming computers, is the same.